Graphene oxide and its derivatives as a basis of functional composites and functional nanocomposites. Hello dear viewers, today I'd like to speak shortly about such new and intriguing class of materials as graphene oxide and its derivatives. As you may know, graphene is an individual single layer of carbon atoms, and in principle you can get this material from usual pencil if you take some pencil lead and tear it off many times with scotch tape. Nobel Prize winner Konstantin Novoselov, graphene discoverer, did it in the same way, but he used highly oriented pyritic graphite. Graphene is one of the most electrically and thermally conductive and strongest material in the world. And it is also flexible, that opens up many perspectives for its usage. Nevertheless, pure graphene is not usually suitable for nanocomposite formation because it has a very low level of defects, so it's difficult to form chemical link between graphene and other materials. Other disadvantage of pure graphene is that size of a single graphene flake is usually very small. So, and it is small in such a way that you can't, for example, make a display electrode for flexible touch screen. So, if you want to make flexible electronic device, you need to do something with graphene to make a large film. This film could be not such conductive as pure graphene, but it should have good conductivity and large size. One of the ways to form large area conductive film is to synthesize a graphene film on the substrate with a catalyst layer by chemical vapor deposition process. Drawback of this process is that it requires relatively high temperatures from 600 to 900 degrees centigrade. So flexible polymer substrates can't be used, and so using chemical vapor deposition you can't, for example, make a display for something like Samsung Galaxy Fold or Huawei Mate X. Other way is to use a group of wet deposition methods like drop casting or spin coating, but in this case you will need to dissolve graphene in some solution with fusor formation of suspension or colloidal solution, and you will face with such feature of pure graphene as coagulation. So it's the agglomeration of individual graphene flakes into one big particle. To avoid this feature, you need to form graphene derivatives that is known as graphene oxide due to the presence of oxygen-containing functional groups. Graphene oxide is usually formed through a process called Hammer's method, representing the addition of potassium permanganate to a solution of graphite, sodium nitrite and sulfuric acid. Final product, graphene oxide, have a hydrophilic nature, so it can be easily solved in water or other polar solvent. After deposition of graphene oxide film, it should be reduced to form conductive layer. There are many ways to reduce graphene, so it can be chemical treatment, thermal treatment, or other process. Depending on the reduction process and parameters of this process, you will have different reduction rate. But you can form a big, relatively big film. Reduction removes functional groups from the edges and surface of graphene oxide flakes. But if you don't fully reduce graphene oxide, there will be some functional groups that can interact, for example, with beer molecules, light-sensitive particles, or polymers. So in the end, you can form, for example, conductive or light sensitive composite, or for example, biocomposite. So now we will shortly observe wet deposition methods. Scientists from all over the world use different methods, but the most known are drop casting, dip and rod coating, spin coating, aerosol deposition, and inkjet printing. Drop casting is the easiest process. You just put a drop of graphene oxide solution that is usually dissolved in water, but you can use other chemicals, other solutions like tetrahydrofuran, for example. You just put a drop of graphene oxide on the surface of your substrate. You can use different substrate with this process. So substrates can be varied from conventional silicon dioxide substrates to different flexible polymer substrates, for example, polyethylene terephthalate. Important moment of drop casting is that the drop should fully cover the substrate. And to vary thickness of the film, you can use many depositions, and you can also make different concentrations of the graphene oxide solution. Important fact is that next deposition should be done only after full drying of the previous layer. Main drawbacks of the drop casting methods are high roughness of the final film and drop casting is the easiest process. You just put a drop of graphene oxide solution, usually in deionized water, but you can use other chemicals like tetrahydrofuran or something other. So you put the drop of graphene oxide containing solution on the surface of your substrate. You can use many different substrates, from conventional silicon dioxide to different flexible polymer substrate like polyethylene terephthalate or something other. And the drop should fully cover the substrate. In this method, it's one of the drawbacks of this method, you should use relatively large volume of the graphene oxide containing solution. To vary thickness of the film, you can use different concentration of graphene oxide solution, and you can make more than one deposition iteration. Important fact is that next deposition should be done only after full drying of the previous layer. Other drawback of the drop casting method is relatively high roughness of the final film, so it's not suitable, for example, for flexible electronic applications. Rod coating is very similar to drop casting process, but after you put the drop on the surface of your substrate, you should use a rod to form a thin film. So you put the rod into your drop and move it along the surface of the substrate, and you should control the height of the rod over the substrate surface, and you should control the speed of the rod movement. Due to the meniscus formation, you will get a thin and relatively good film with low roughness. Lack of this method is that you need to very accurately control the distance between the rod and the substrate and the movement speed. So you need to use some equipment with digitally controlled motors. Next method is deep coating. In this method, substrate is vertically put into a container with graphene oxide solution and then put out of the solution, but very accurately and with relatively low speed. Pulling is done with controllable speed, so a thin layer of solution is formed on the substrate surface, once again due to the meniscus formation. In the deep coating method, you can easily control thickness of the formed film by varying number of depositions. Disadvantage of this method is relatively low speed. The drawback of this method is relatively low speed. The limitation on the size of container for graphene oxide solution, and you once again need some special equipment to control the pulling speed. Another process is spin coating. It's a well-known process came to nanotechnology from microelectronics. In this process, solution is deposited on the surface of the substrate, which is held on the top of a chunk within the spin coater. It's important that the solution covers the substrate completely prior to the spinning. So once again, same as in drop casting. Then the substrate at the spin coater accelerates rapidly to a high rate per minute speed and held at the speed for some time. When the spinning is complete, the thin film has been formed through a combination of liquid flow and evaporation processes. Depending on the type of on the solution and characteristics of the solution, for example, concentration, you may require to use different deposition, different rotation speeds, and you will also need after deposition treatment, for example, heating or ultraviolet treatment. Advantage of this method is a relatively high deposition speed and formation of the film with relatively low roughness. But drawback is that you need to use large volume of the graphene oxide solution. And you also should accurately control the spinning speed, so you need some equipment. Aerosol deposition is a technique that is very similar to painting process in car industry or in scale modeling. But instead of paint, you should use graphene oxide solution. In the spray coating process, a spray solution is directed to the substrate by an atomizer. The atomizing can be accomplished through different techniques ranging from simple air blasting to more advanced techniques like ultrasonic or electrostatic atomizing. So in this method you can form relatively large films with high speed and relatively low solution consumptions. But the drawback of the aerosol deposition method is that you need to accurately control the attributes of the solution, because if the individual graphene oxide flakes agglomerates, so there will be different defects in deposition. So the form of the needle in air blasting, or in the form of the needle in atomizer can change, and it's not very good for deposition, because you will have different deposition defects. For example, large drops on the surface, so it will have high roughness in this case. And another one well-known method is inkjet printing. So in this case you just need to change paint solution in your inkjet printer to a graphene oxide solution. But important moment is that solution should be with very similar characteristics to the original paint. So especially important is surface tension. So the main drawback of the inkjet printing method is that you need to very accurately select the composition of the solution, and because in other cases you can't you can't make good patterns. But the inkjet printing method have some advantages, like that you form a film of graphene. You form a graphene oxide film locally, and you can make each pattern you need. And it is a relatively fast method. Okay, the film is formed. One small addition is that this film must be carefully dried to avoid crack formation. Then the formed film should be reduced with one of the methods mentioned above. So it's thermal reduction, chemical reduction, or, for example, light-induced reduction. In case of chemical reduction, the hydrogen vapors are usually used, but in this case you can only reduce full film, so you can't reduce some sophisticated patterns on the film. And also hydrazine is very toxic material, very toxic chemical, so the process is not such easy. Other process is thermal reduction, but it has such a drawback, is that you need relatively high temperatures. So temperatures ranging from 300 degrees centigrade and above. So in this case you can't use flexible and polymer substrates. That's the main drawback. And during the last decade they became a popular method is light-induced reduction, and especially laser reduction. In this case of laser reduction, you can form each pattern of reduced graphene oxide film you need, and you can also control the number of functional groups and even the type of functional groups if you use, for example, ultraviolet irradiation or femtosecond laser. So now let's speak about which composites and functional composites you can make based on graphene oxide or reduced graphene oxide. So one application of graphene oxide and reduced graphene oxide is gas barriers and membranes. It's interesting that high gas barrier properties of polymer nanocomposites can be improved with two-dimensional fillers that can be oriented in polymer matrix to create a tortuous path for gas molecules. So you can put flakes of graphene oxide or reduced graphene oxide into polymer and give them orientation that will improve gas barrier properties. So for example, it's usually used graphene oxide or reduced graphene oxide mixed with polyamide. Another application is water treatment. So graphene oxide based membranes are considered as promising material for water treatment application because of their high water permeance and stability in the water. As a result, for example, graphene oxide sheets in polydopamine modified PETs substrate with tannic acid and thiamine amino acid used as cross-linking agents demonstrate water permeance with about 100% of rejection for rhodamine B and methylene blue. So it's very clear water that is just fully cleaned from dyes. Other big sphere of graphene oxide and reduced graphene oxide application is different actuators. By using polymer nanocomposites containing graphene oxide and reduced graphene oxide, you can form small actuators that can act as an artificial muscles in flexible or in just small robots, and these composites can be actuated through a humidity, so you can make water robots through the thermal or light actuation, so you can make relatively easy schemes of control for these robots, or just electromechanical actuation, so the artificial muscle is actuated through the electronic signal, and in this case reduced graphene oxide electrode is made on the surface of the polymer, and it works as such well-known device as ionic polymer metal composite, but in this case it will be ionic polymer graphene composite actuator. So it's one of the development direction for the different robots development. Corrosion resistance. Graphene derivatives show promise for anti-corrosive polymer containings because of their 2D morphology and high chemical inertness. So, corrosion resistance. Graphene derivatives show promise for anti-corrosive polymer coatings due to their 2D morphology and high chemical inertness. Polymers alone are permeable to chloride, sulfides, water and other chemicals that would be harmful to the substrate metals, but graphene and its derivatives could be used as fillers to prevent the diffusion of harmful material to a metal surface or even promote the generation of the passivation layer. Another big sphere is energy storage. So reduced graphene oxide is a promising material for many energy applications such as supercapacitors, lithium-ion batteries, and for different stretchable electronics, flexible and stretchable electronics. Because of the long cycle lifetime and high power density. So using graphene oxide and reduced graphene oxide, you can form capacitor. You can form a thin film, but with very high roughness. So you will, in this case, you will have a very high capacity of the capacitor. And once again, a very interesting area for graphene oxide and reduced graphene oxide application is sensors and biosensors. In this case, especially reduced graphene oxide is a very promising and interesting material because you can relatively easily immobilize different biological agents to the surface or edges of graphene oxide flakes. And this material, reduced graphene oxide, is also conductive, so you can get electrical signal from different, for example, from different pathogens that then can be turned easily into a signal, for example, for your smartphone. So you can make a biosensor to find some impurities or illness markers in your blood or in your tears or in some other physiological liquids. And as a material for chemical sensors, reduced graphene oxide show very good characteristics, for example, for methanol vapors or for ammonia vapors. So you can make relatively cheap and sensitive sensors for these gases. That is very important for different manufacturing areas. Thank you very much for your attention. I'm glad to speak shortly about such an interesting material as graphene oxide and its derivatives like reduced graphene oxide.